Okay, let's start anyway. I would like to introduce you to Alex Acero. He's a principal researcher at Microsoft in Redmond. He's in the area of speech, but he also worked in the areas of image processing some time ago. He's working with Microsoft since 23 years ago. Right?
No, 1994.
1994. Okay.
That's still a long time. Okay, thank you. So I was initially planning to talk about spoken language processing and how about you build one of these systems. But I have a bunch of slide decks from other talks, and yesterday at lunchtime, it seemed that like a few people were interested in more core machine learning. So I will start with this because I think it may be of interest to a number of you. And we can switch back and forth to any other topic. And by the way, feel free to interrupt at any time. I like this to be interactive. So let me start by talking about deep neural networks for speech and image processing. And I'll give you a brief introduction to neuroscience, talk about artificial neural networks in general, and then describe what these deep neural networks are, which is the latest generation of neural networks and its application to speech recognition. So I'll start with a picture of, this is me with more hair and less weight back in 1990 in an office in the basement of Carnegie Mellon University. And the reason I include this is because that's the year I got my PhD on how to make speech recognition systems robust to background noise. That was a problem back then that we had identified when we started working on speech recognition systems that work well when you were using a close-talking microphone. And once you put the microphone far away, things started to fall apart. Well, it turns out that's still a problem today. So it doesn't seem like I solved it, unfortunately. But at least the community has made some progress. One of the things that I want to point out is one of my office mates, Yoshiaki Oshima. We started the PhD at the same time, and he started working on neural networks related stuff. So I finished in 1990, and he was still there. And I think it took him like 2 or 3 more years to graduate, and even then, didn't make much progress. So since then, I never enjoyed neural networks. So this is just to tell you that I was very skeptical of neural networks because I had seen him suffer for many, many years as an office mate. Meaning, okay, neural networks, there's obviously something there, but there are lots of other problems because it's like tricky to train. So this is just to tell you I was never a friend, but now I'm a believer. So you may be interested in why that was true, right? So let me start by describing briefly what neurons are and the motivation for neural networks. What was the first generation of neural networks and the subsequent generations? This is a diagram of a neural network. And the interesting thing is here you have the nucleus with all the dendrites. You could view this as inputs to the system. And this is the big output that it's connected to other neurons. There are lots of neurons in the human brain, 100 billion roughly. And each one of them is on average connected to 7,000, meaning a synapse is like a joint. Maybe another axon comes and joins here as input. And on average, there may be like 7,000 inputs. One interesting thing is that neurons are non-deterministic. So what they do is they emit spikes depending on how much they are active. So even if you put here the same inputs, the output here is random to some extent. Of course, the more inputs that it gets excited, the more spikes it will generate per second, but it's not exactly the same. Same thing in the input as well. They're also slow. I mean, they often take like 1 millisecond to react. So this doesn't seem like a very powerful computational machinery. Yet, we obviously have 100 billion of them here, and they seem to be doing something right. So what is it? Well, one of the things, if you look at the systems theory point of view, what is the input and output relationship? You see a function like this. So you have all the inputs, V's, and you multiply them by weights. And then you subtract some threshold, which is the minimum threshold that neurons need to get activated. And then you go to this function, which is called the sigmoid nonlinearity. And you would see some function like this. This is 1 and this is 0. When the inputs, the weighted inputs, are above some value, then the neuron fires, and it's the same value here or here. Doesn't matter, it's on. And when it's much more negative, it's off. So it's either on or off with some region in which it's changing. So this sigmoid nonlinearity has been the main function that people have been using for neural networks. neuroscience is something that I became interested just recently because we were doing some experiments with the next generation neural networks, deep neural networks, that I will describe later on, and realized, well, this worked quite well, but is it possible that we can learn even more? So I've been reading even some papers on figuring out, well, what's the difference between the brain of a human and some of the predecessors, or monkeys or chimpanzees, which we seem to evolve from. There must be something similar, yet also something different. And if we learn this, even from the computational point of view, we may be able to come up with discoveries that advance health and medicine, like diseases like Alzheimer's that impact our brain. If we understand how our brain works and we can build systems that leverage those capabilities, we can go back, perhaps, and make advances there. So one of the basic rules that was derived in the 40s by a person called Hebb derived something called the Hebbian rule, which is neurons that fire together wire together. That was the basic algorithm for learning that up to date, they think that at the high level is roughly right. So if the input of the neuron and the output of the neuron are on at the same time roughly, that means that the weight between the two neurons is going to get bigger. That mathematically is not so easy to describe, right? This is also something that I found interesting. If you look at the number of synapses or connections that the human brain has, we start at this level, and then we peak, we increase the number of connections up about 2 years old. So a 2-year-old has more synapses than all of you, because then we decrease. But the interesting thing is that this is not steady. There are always creation of synapses and destruction of synapses. In creation, it's just as important as destruction. So creation means that you create random connections between neurons, just completely random, and then using this rule, if you see that some inputs and some output are correlated strongly, those connections will get strengthened, and they will remain. The ones that don't seem to correlate, they disappear and die. So when you happen here, after you reach adolescence, you have the same number of connections because you create some and you destroy some, and roughly you keep active about the same. That's one of the reasons we can learn new concepts, because we create new synapses where none were there, and we increase those weights, and other things we forget. So those are very interesting things. So let's go from the motivation of neuroscience to the artificial neural networks. And I guess a milestone started in 1958. I'm going to give you a little bit of a historical perspective because I find it useful. Otherwise, we may repeat the mistakes of the past with the next generation, and we may also not know what to do next. So a lot of that, and probably some of that, is something that you've studied in your machine learning classes. But I will describe them here briefly, just focusing on some of the big transitions from one generation to the next generation. So in 1958, Rosenblatt defined the linear classifier. Pretty simple thing. So you have, let's say, a two-dimensional input vector, V1 and V2. Of course, you could do this in multiple dimensions, but just so that it's easy. And you have classes, one class on one side, one class on the other side, and you want to find a dividing line. So that if you can compute, in this case, this function with these weights equals B, that's the line that is in the middle. If it is bigger than B, you say, well, it's a triangle. If it is smaller than B, well, it's a circle. And it turns out that you could define this as this function, as a sigmoid function, like that. In this case, it's separable, so it doesn't really matter what the shape of this is, but you could find a non-linear function like this. And that's what he did for the perceptron. Interestingly enough, this was motivated by, in part, the behavior of the human neuron system, right? It's the same kind of function. Where did it come from? Out of thin air. He just thought this works, let's use it. Which is part of the reason why I wasn't that excited about neural networks at the beginning. So, well, why? Just because humans have this function, should we use it too? And we don't quite understand why, but it seems to work, so okay. So how do we do the learning here? So what we want to do is, let's say we have 3 inputs or 3 weights and produce 1 output. We want to compute the errors, the sum of errors, if we have a number of samples, t, let's say, and we have the h is the value of the network, And we have some learning examples. We have labels L. So we want to compute the distance and compute the error. Ideally, if our network has learned properly and the problem is linearly separable, this should be 0. The error should be 0. Because problems in general will not be linearly separable, there will be like some points that fall on the wrong side of the line. That's just what happens. This may not be 0, and that's okay. But you still want to find the weights that minimize this error. This seems to be like a reasonable criteria. Again, this is the function here, and given by this sigmoid, which, by the way, this is the equation. 1 plus e to the minus x raised to the minus 1, so that when x goes to infinity, this term is almost 1 divided by 1 is 1. When this is minus infinity, this term is very large, so this goes to 0. That's essentially what it is. So one possibility would be to say, well, how about if we do a gradient search? Because this function is nonlinear. You can't just take the derivative and equal to 0. How about if we do a gradient search? So that the next set of weights is this previous one minus some constant times the derivative of the error with respect to the weight. If you take this function and we take the derivative, we will see it's 2 times this plus the derivative of the error term with respect to the weights, which if you do the math, it turns out that it's this product of these two things. Or in other words, this. And this makes sense. Like in this region here, if you take the derivative of this is 0. So the derivative is 0. Same thing here. And there is a non-zero component of the derivative in this area, which means as long as you are in this part of the curve, the derivative will give you something. But if you are here or there, nothing. So another problem to consider here is like this function will have many global optimum in general. In this particular case, I have you here just 2. So if you start some point here, it will hopefully converge to this, but not to this. So this is another way of saying that this perceptron algorithm is only going to find a local optimum. It's not guaranteed to find a global optimum. This is a simplification. In general, there will be like lots of optimum, maximum in the function. The vector will be very large. So this is definitely going to happen. But this worked pretty well until a famous paper came in 1969, authored by Minsky and Papert. And Minsky was considered to be one of the 4 founders of artificial intelligence. There was like a meeting in Dartmouth College in the early 60s where 4 big names in artificial intelligence, Minsky being one of them, met and decided to coin the term even of artificial intelligence. So Minsky was very influential. And he said, well, if I have a distribution like this, which is kind of like the XOR, mutual exclusive, where it's not linearly separable like this, I can't find a single line that will do the job. I'd almost need to divide like 2 lines and say, well, do something more complicated. Therefore, the perceptron machine, while it's doing a nice job in a number of algorithms, a number of tasks where things are linearly separable or closely, there are many cases, this is one of them, and there are many others, for which this perceptron won't work. So that was a correct observation, nothing wrong about it. But in hindsight, what happens is that we should have taken that with a grain of salt. That doesn't mean these things will never work. That means that perceptrons cannot handle this. That doesn't mean something else cannot. But because it was written by Minsky and the way people read it is, oh, neural networks are doomed. So forget it. So the first winter of neural networks started. After a number of years in the late 50s and 60s of activity there, let's work on something else. Well, we need to remember why this happened so that we learn our lessons for the future, right? The artificial neural networks, essentially, a few years later, although interestingly enough, something like this without this function was proposed by the famous Alan Turing as far back as 1948. He developed, was one of the luminaries. That's why the Turing Award is the most prestigious prize in computer science these days after Turing, because he invented a lot of things. So he even proposed the artificial neural networks, which is to say, one perceptron was just this part here. just one. What happens if we can put many of them together? Like this is the first layer, so we put many of them, and then we have maybe a second layer, or even more, until we compute the true outputs. If we can do that, then the problem that Minsky and Papert suggested in the previous slide no longer applies. That's also true. That's only true if you have a single layer. The minute that you have more than one layer, you can do, in theory, arbitrarily complex decision boundaries. And in fact, in the Minsky-Papert paper, it was described that way. But people didn't quite focus on that, and they said, it won't work. But this, in theory, could do it, at least in theory. So there was, in fact, the same year that the Minsky and Papert paper came, starting the neural networks into the winter, there was another paper that was hidden, and many people didn't even notice because they had said this is not going to work, right? By Bryson and Hoback, that discovered or invented the algorithm called backpropagation, which many of you may already know. So I'm going to give you a very brief description of how the backpropagation works. But it turns out that it was dormant for many years. People were not even paying attention to it until 1974, where a Canadian physicist, Geoff Hinton, rediscovered it. So he gets a lot of the credit for reinterpreting, rediscovering, and popularizing, even though the original version was back in 1969. And I'll give you, although some of you may already know it, I'll give you a very brief idea of how it works. And the algorithm is very simple, really, if you think about it. It's the same thing. We have here the energy, the error term. We want to minimize the difference between the label and what the output of the neuron has. But in this case, I'm going to have, let's say, 2 layers. The network is more complicated, but just for simplicity, the derivation holds for a bigger network. I'm just going to have 2 layers. These are the inputs. This is the weights of the first neuron. This is the output. And then we have another one here, and then there's another layer. So we want to minimize the errors here, which is the output of this, H21 minus the label. So if this is the function H21 as a function of the H11, H12, H13, and the same thing here with H12 as a function of the visible units. V stands for visible in these things. We want to find the weights here, these weights, how these weights change by looking at the error here. The idea of backpropagation is the error here backpropagates to this one. And that's what we can use to adapt these weights. So if we take the derivative, the gradient just as we did before, but in this case the derivative is more complicated because it has this term here. This part was the same as before, but now this term is because you cannot compute things directly. This is not fixed. This before was the visible units, and they were fixed. They were just the observations. That's no longer true. That's a function of the previous ones. So we need to replace with this term where there is the derivative of this value with respect to this, which is, again, same thing. So this is the idea of backpropagation. The error here backpropagates here until it reaches down and then up. But the idea is the same thing. We want to find the weights of the system that minimize the error between a set of labels that I get and the output of the system. And we tweak the weights, all of the weights of my network to minimize that. And the way we do is the chain rule, basically. We take the derivative, we propagate it, and mathematically, again, it's very simple. Same thing. We can get stuck into a local optimum if we do this. Only that here, because of this looks much more ugly. There's like tons of local optimum that you can find in this surface. And the problem of convergence is much more difficult in theory. Although, if you do this, you will converge. If you have the right weight here, you will converge to a local optimum. So that's the algorithm of backpropagation. And there were many papers. For a while, it was just Hinton that rediscovered in the 1974 paper backpropagation. And he was one of the few people that was working on it until the 80s. There was some activity, but not much. And definitely nothing in speech recognition. Speech recognition is the area that I was following closely for my thesis and ever since. And there was a flurry of activity of using neural networks in speech in the late 80s. That's what I call the classic period. And the interesting thing, they use neural networks for ASR, time delay neural networks where the inputs get shifted and the weights are shared. Recurrent neural networks where the output of the network at the previous time was also input for the next time, so you can have somehow history that way, and a number of other variants. And they actually worked pretty well. So back in the early 1990s, this could have been the technology. But the second winter of neural networks came. This time for a very different reason. HMMs, or hidden Markov models, were the dominant technology in speech recognition since the mid-70s, but neural networks almost took over, but never did it. And the reason is that the artificial neural network systems that I described didn't do better than the HMMs, but did about the same, roughly. That's not a reason to change the incumbent. You want to only change what you're doing if it's substantially better or has other advantages. And this is about the same. But unfortunately, HMMs were a lot faster to train. So training hidden Markov models was something that was much simpler. You push a button, the system worked. You didn't need to tweak anything. With the neural networks, you had to adjust the learning rate of, in theory, every single neuron, or at least figure out how you're going to do it. You need to initialize it properly. If you didn't initialize it properly, you converge to a bad local optimum. So the training process was much more finicky, more picky. That's when I saw my office mate back at Carnegie Mellon struggling, because there were all these initializations. So you have this, you need to find the right learning rates for all of the neurons. You need to find the right initial point. How do you do that? In a multi-dimensional space with lots of inputs, it's not easy to do. And on top of that, and just that was the worst thing, to train this, it would take forever. You push the button, and the program probably crashed well before it was finished, because ran out of memory, ran out of time, someone unplugs. It just took weeks in some cases. So that's the winter of ANN. If you think about it, and again, it's important because if we don't learn the lessons of history, it may happen to us again, is that the reason why this happened was very different than in the first case. In the first case, the reason is because someone said that the power of the model was not strong enough. Now, someone later said, well, that's not true. This model could have parameters that are powerful enough to do these arbitrary decisions. But training is difficult. And this is the renaissance after the classic era. Here I have a picture of Geoff Hinton, who is probably credited with being the main person behind neural networks, if you average over decades that he's been working on it. And back in 2006, he coined the term deep belief networks, or deep neural networks. And you will see both the DBN and DNN. People don't like DBN because there's also another acronym, dynamic Bayesian networks, which are very different animals. So that's why we call it deep neural networks. Before I tell you what they are, let me also tell you that the first time I heard this, I thought it was very presumptuous to call it deep. Because what is the difference? I mean, it's called deep because it has many layers. I mean, just because your parameter n is 5 instead of 2, you want to call it something different? I mean, I thought it was a little bit too much at first. Again, I was coming from the skepticism of having had an office mate that almost cried on my shoulder once in a while because things were not working. So I thought at first it was presumptuous, but you know, it's okay. One of the guys in my team one day came, he was going to NIPS, and said, well, there is this new thing, deep neural networks, and I think this is going to be it for speech too, and I want to spend some time on it. But by the way, before we do this on a speech, I want to use it on this MNIST task. MNIST is a task developed by NIST. I don't know if you know about NIST. It's the National Institute for Standards and Technology, based in the United States near DC. And essentially what they do is they often come up with standard test sets. That's why they do standards. They are also responsible for your atomic clock precision. They have an atomic clock in Denver, Colorado, and others, but that's a separate story. So they developed this task, which essentially is like a collection of handwritten recognition numbers. In this case, I show you a 4, but you can imagine there are lots of other numbers. And the goal is to build a system that can look at this image and say, oh, that is a 4. It's not a 6 or a 9, let's say, in this case. A 9 sometimes could be confused because it's not that different than a 4 if you think about it. So that was that task. And he came and said, well, I want to do this. I said, well, but you're in the speech group. Why do you want to look at handwritten recognition? And that's one of the things that is good to have the freedom of researchers. In the end, I said, okay, go ahead and do it. So, well, I need to understand this algorithm first on the task that Geoff Hinton has proposed. Because if I don't, it's going to be very hard for me to move to a new application with all these weights and all these things. Said, okay. So he started working on this task, which is the one that Hinton started publishing. And, well, I haven't told you what deep neural networks are, but essentially what it is, at the very high level, is that you do this called pre-training. And pre-training means, and then you follow by backpropagation. So pre-training means we know that these neural networks are very picky and finicky to the starting point, the initial condition. So if you use this pre-training algorithm, and I'll tell you what that is in a bit, it's going to converge to a much better initial point. So, and that's, as we know, very important. And then they do backpropagation, also call it fine-tuning. The reason why it was called fine-tuning is because the initial point is actually already a pretty good point. And it's been developed using a theory called restricted Boltzmann machine, RBM for short. And that initial point you can update a little bit by doing backpropagation and get the final result. So that's the high-level idea. He got very good results, and most of the reason why he did get very good results was the very good initialization. So there were like 3 problems, if you remember, why the second winter of neural networks started. Is initialization is very difficult when you have input features that are many hundreds of thousands. It's just you don't know how to do it. If you have many weights, this provides good initialization. Convergence speed. Well, it turns out that that was a problem in the early 1990s. But since then, Moore's law had helped us with faster and faster processors. So some of the problems that we had before are much less of an issue. Now computation is less of a problem. And the final thing is the training algorithm is kind of picky. Well, because of the initialization, that was less of a problem. So let me tell you what is a restricting Boltzmann machine. And this is one of the reasons why I was a convert. I hated neural networks. And then once I saw this, oh, okay, now we're talking about something different. So why? Why is that? I think most of that is in this slide and the next one. So what Geoff Hinton said is, I'm not going to tell you this sigmoid that I pull out of thin air. You don't know what it is. I'm going to derive a probabilistic model of the inputs and the outputs that will happen to have a nice property of showing the sigmoid. But the key thing is the original formulation. So here you have a set of V is the visible vector. So this is a vector with many observations. H is a vector of hidden layers. This is like the first layer of the neural network. So what the probability distribution, the joint probability distribution of both has this form. It's an exponential model. Z is the normalization constant here that will mean that it adds, this is a true probability distribution. And this is the energy term. It's called the energy term. And the energy term is given this way, which is nicely linear. It's linear on V, it's linear on H, and it has a joint between the two. So here this is vector, and B is a set of, it's another vector that you presumably would learn. This is the hidden with another vector C, which is another set of coefficients. And here we have the matrix W, and it's called W not by accident. It's the same W of the weights that we saw before, as you will see. So this seems pretty simple. It's like a linear everything. This is log linear. So, we had a lot of experience with maximum entropy models, for a lot of applications in machine learning or log linear models. So when I saw this, I said, well, this is interesting. I would not be surprised if this is good. So what? But we've been using this. What happens? Well, let's look at the marginal. What is the probability of the hidden if you know the visible? So you need to put this term, the z constant goes away, and you divide by the probability of the visible, which is this, but sum over all the h's. If you express the energy function here, you get this, no different. But look at this term. This term is not a function of h. You can cancel out, so it disappears. And once you have this here, it turns out that h is binary. So all these systems are binary, 0 or 1. And if you assume that v is also binary, so the inputs are 0 or 1, it turns out that you can prove that this is just a product of these guys. So all of the h's are independent of the other h's. And this function here is like, whoop, what is this? This is the sigmoid function that we saw before. So the reason why I got excited is that before neural networks, at least what I had seen, is that you use this sigmoid function. Why? Because it sounds reasonable, seems to do a good job in perceptron, linearly separable data, and it seems to be what the human brain is using. Okay, but that wasn't satisfactory enough. Now I can see, oh, this function, yes, may have those other motivations, but it also comes if you have this model. So if you have this model, there may be other things now that we can do. Interestingly enough, if you do the same math, you can also compute things in reverse. If someone gives you the set of hidden values, you can also compute what is the probability of the visibles. So you can interpret the model too. It's not just you put things as input and numbers happen, and in the end, you see if you got it right or not, which is not very intuitive. But also, if you have a vector of hidden values, you can see, oh, with those hidden values, what kind of input is the most likely thing that would trigger? And it's also a sigmoid. Oh, that's kind of interesting. And it's also independent. So you can go forward and backwards. Sometimes what we have are visible, for a neural network where the inputs are zeros and ones, this applies to the next layer and the next layer and the next layer. But it could be that the very first layer, your input is not 0, 1. It's not binary. It may be real numbers. So what do? Well, we are used to assume that they are Gaussian, right? So one possibility is to modify the energy function this way, where we've added this quadratic term. The rest is the same. So if we make that, and you do the same derivation that I showed before, guess what? You still get the same thing. So that sigmoid function, this sigmoid nonlinearity, is the same as before. Doesn't matter whether the input v is binary or is Gaussian. The posteriors of the visible units, so the equivalent of this, now is different. It's Gaussian, of course. But it's also very simple and nicely expressed. So now what this says is that even though we have not changed anything, the function is still kind of like sigmoids like this in both cases. So it almost feels like we haven't done anything. It turns out that we have a much better understanding of what it means and why. It's almost like now we know not just the output of the system, but also what is going on inside the system. And as a result, we may be able to do other things. For example, one typical thing that we might want to say, if we have the distribution of the visibles given these hidden values, these parameter values, we may want to find the maximum likelihood estimate of the C, B, and W that maximize the probability of the observations. That sounds like a reasonable thing to do. And of course, because what we have is the joint distribution, we need to sum over all the h's and do this thing. And this is something that, because we now can interpret things probabilistically, we may be able to attack this problem. Even though, of course, there's a little problem, which is now this is nonlinear, highly nonlinear. So that may not be straightforward, but at least one can try to do this. And in fact, there is another algorithm called contrastive divergence that is doing essentially a maximum likelihood estimate of those parameters, an approximate maximum likelihood estimate. And this is the way it works. Let me give you first the intuition and then the formula, because it's actually also quite simple. What we want is to have the weights from one iteration to the next to be the difference between the correlation between the visible and for the data that we have and what the model would provide. So if my model tells me this and my data tells me is that, well, I want to increase the weight for the next iteration. Once it's converged, what you expect is that what the model tells you and what the data tells you is the same. That's kind of the equilibrium point. That's the intuition. The true derivation is much more complicated, so I'm not going to show it here. But the way it works is we initialize this. This is my input samples, the input data that I want to train in. And from here, I sample from a distribution. And I pick from this distribution, because it's just sigmoids, it's easy to, I just draw some points. From these points, I can go up and now down, because it's the same formulation, the sigmoid going down. I can sample back, and one and so forth until this is like a sample from the model. And I do this many times. If I keep doing this up to infinity, this would be a true sample from the model. It turns out that I don't need to do that. If I just use this, it seems to work empirically. There is no mathematical proof that that's true, but it converges. So essentially, we start with some random values. We go up and down, up and down, up and down. And every time we change the weights, and we do several iterations. And that's how contrastive divergence works. And going back here, that's an approximation of this. So we'll find the W that maximizes approximately this. That's probably a better initial condition than just setting the weights at random. And that's very important to get a good initial condition. So the training, again, is we use this restricted Boltzmann machine algorithm, RBM training, which is an approximate maximum likelihood algorithm for finding the weights in this network using contrastive divergence. And once we have that as initial condition, we use the backpropagation algorithm to go and fine-tune. So now let me tell you the experiments that we've done for speech recognition. So after this work was done in 2006, 2007, and this researcher in my team, Li Deng, became interested in it. He went and reproduced the results that Jeff Hinton had done for handwritten recognition digits, and he started applying it for speech. So what is the architecture of a traditional speech recognition system? I have the hidden Markov model, and GMM is Gaussian mixture model. The way it works is like we have a hidden Markov model like this one state, another state, and at every time frame, the system could stay in the same state with this probability, or go to the next state with this probability, and so on and so forth. So every time there is a time frame, typically every 10 milliseconds, the system will be in a different state. This is when we're running it in generative mode. And this is the internal hidden state. It's not visible. Once you're in each state, there is an output vector that is shown, that in this case is a spectrogram. This is time, this is frequency. And this output is often represented as a mixture of Gaussians. So if I'm in a given state, I look at the probability of this mixture of Gaussians, and I generate this spectrogram. This is called a spectrogram. So this is roughly what you would see used in most, this is the high-level idea of most speech recognition systems, use an HMM. Typically, we train them with maximum likelihood initially, and then we also fine-tune them with discriminative techniques, so that this is a generative model, but what we want is not to have an HMM that generates data well, but also that discriminates one class versus the other. So what is the difference with this context-dependent deep neural network HMM? This part is the same. We still use an HMM. We have not replaced it. But now, once you're in each state, rather than saying, I'm going to generate the spectrum with a mixture of Gaussians, I'm going to generate this with a network like this, with a deep neural network. So in this case, this spectrum goes here, some layers, and this here are the probabilities of the different states. So this now seems more complicated. If you think about it, this is a way of saying I can represent these output probabilities with a more sophisticated technique than just a mixture of Gaussians. And this is good because they are sharing. Anytime there's pooling in the training, all of the weights here contribute here, and so on and so forth. So you can compute much more sophisticated functions, yet you don't have as many parameters. Yes?
Sorry, it's the same DBN and DNN?
Yes. Yes, I just prefer to use DNN because not to confuse it with the deep belief networks. But yeah, basically it's the same. By the way, any more questions? We'll have a chance after I finish this to go for more questions. So this is the high-level idea. Replace the Gaussian mixture for the output distribution of the HMM by a deep neural network. There are a few tricks that we had to do. This HMM is using a generative model. So it's expecting something like this. What is the probability of the observation given that you're in that state? But it turns out that because the neural network is a discriminative model, it's going to tell you the probability of the state given the observation. It's like flipped in a sense. So we can use Bayes' rule to decompose it that way. And because this term is a constant, if you've seen the observation, that's true for all of the states that you're searching for. So all you need to do is normalize by this guy, which essentially says that we can convert the generative model into the discriminative model that the deep neural network is into a generative model, as long as we add this. We normalize by how likely are these states. For example, silence is a state. Like states could be all the phonemes, and silence is a state that is happening much more often than all the sounds, just because a lot of the data that we use to train them has a lot of silence frames. So we need to divide by this, otherwise this would be overestimated. But if we make that change, we can plug it directly into our speech recognition system. And the classes here are what we call Xenons, which essentially is a context-dependent version, meaning rather than we have typically for each phoneme, we have three states. The beginning part of the phoneme, which is like the change from one phoneme to the next, the middle part of the phoneme, which is the steady state, and the last part of the phoneme, which is the transition to the next one. We often use context-dependent, meaning a particular phoneme will change depending on what the neighbors are. Like if you are between nasals, let's say, that phonetic realization is going to change quite a bit. So you want to use states or distributions that depend on the phonetic context and other things too. So this is what we do. It turns out that we can use more. We had 6,000. We can use more with this technique than what we had before because it's a different model. And this is the new name. So how well does this work? Well, before let me describe a little bit of the experiments. Here are some of the folks. This is Li Deng, the person that I mentioned that started the work back in 2008 or so. And these are a few other folks, including people in Redmond, Dongyu, and in Beijing, Frank Seide and Gang Li. So there are non-Chinese people in the Beijing lab if you're interested in going there as well. And what they used is a standard task called switchboard. Switchboard was one of the tasks that were proposed by DARPA, the United States Department of Defense, and essentially was like try to understand how speech recognition worked with casual conversational speech. So the way it was collected is that they asked people to call each other and they were given a topic. So talk about the presidential election or like the Euro crisis or whatever, and then they start the watch and they start recording. And then you can talk about anything you want. Oftentimes this is just a conversation starter because people would say, okay, before we start there, just a social courtesy. My name is this, I live here. Oh, you live there. My cousin lives there. So sometimes the topic is not really the topic, right? But the thing that is in common is that it's telephone conversations and there's no system involved. It's just person to person. So it's natural. When you talk to a machine, you tend to change the way you talk. But when you talk to another person, you talk quite differently, much more naturally, right? So this data was collected to test how systems can handle conversational, natural speech, as opposed to the speech that is more robotic. When you're talking to a machine, you articulate more, you speak more clearly, you speak more slowly, but then, when you talk to these people or you talk to the system, sometimes you don't do that. So there's a big mismatch in the distributions. So that's that data set. It had over 300 hours of training data. And I don't know, how many of you have experience with speech recognition? Could you raise your hand so that at least I have some idea? So like, you know, maybe 1/3 of the audience. So I will at least, this is too much detail if you don't know about it, but if you know about it, you may recognize what all these acronyms, SOUP, PLP, and others mean, okay? But this is just the HLDA, mean and variance normalization. You may be familiar. Otherwise, don't worry about it. For the purpose of this discussion, it's not that important. Other than this is kind of like the state-of-the-art feature that people typically use. This is, again, all the distributions that we model, over 9,000 different distributions, depending on the phonetic context, left to right hidden Markov model, so that they move in like time in the same direction. You don't go back in time. And we use a typical baseline, which has 40 Gaussians per state, a mixture of Gaussians. And a discriminative training process boosted MMI, maximum mutual information. So that's just to say this is the typical baseline that you do for like a state-of-the-art system. Then a recognition, in this case we use speaker-independent single pass. Many people in speech recognition, to squeeze the last drop of accuracy, will do several passes. So you do one pass, now you say, well, now that I've done this, let me do adaptation, because I know that the speech at the beginning and the speech at the end is the same speaker. Adapt there, and then take a second pass. For this experiment, we didn't do that. We used the Hub 5 2000 switchboard development set and evaluation sets RTO3, this is 2003, and another corpora. So again, if you don't know about this, this is just for you to know that we use a bunch of standard publicly available speech corpora that the speech community has been using for quite some time. And we also use our best ever multi-pass baseline, where it does all the passes that I mentioned to you before. With Rover, MLLR, gender-dependent systems, vocal trial-led normalization. Again, that's all the acronym SOUP. Just to tell you, if you know about this, then this will mean something to you. If you don't, just to say, well, we use our best system, okay? We didn't try to come up with a new technique and test it on a handicapped small system, which oftentimes you see in papers. So we said, no, we normally, when we review those papers, we don't give them good marks unless the user even clearly states this is some interest tip. If you're not using the best possible system for a baseline and you're claiming your system when you write a paper is better, your reviewer is going to be very unhappy. So if you're using the best possible baseline, say it. And if you're not, be modest. Say, well, I didn't have time, I didn't have the resources, so I cannot claim this will work better on this best system. But at least be honest, and the reviewer will be much more sympathetic with you than if you claim, oh, 40% improvement, oh, I'm so good. And I say, well, I use a crappy baseline. Reject. So this is on this test set. Here we have the Gaussian mixture model with 40 mixtures, maximum likelihood. And this is the error rate that we got. Once we do BMMI, which is this discriminative training, we got from 30 to 27%. And we tend to look at that as the relative error rate reduction. So from 30 to 27, there's roughly a 3% error rate reduction absolute, or roughly a 10% relative error rate reduction between here and here. And these discriminative techniques have been going on for like a decade or so, and it took a long time to get them work, and we got 10%. In other fields, with that 10% improvement, relative improvement, why you're so happy about it? I mean, it doesn't seem like that big of a deal. Well, unfortunately, that's the world of speech. Every little percent requires a lot of sweat. It's not easy to get. So then we tried this system with 7 layers. So we call it deep. In this particular case, it had 7 layers. And so how well did it do? Drum roll. So it got 18.5%, which is a relative reduction of 33% over this number. That's like, I've been involved in speech since the mid to late 80s. And normally, the last time I saw a 30% type style reduction, error rate reduction relatively, was back in 1989. That's when Kai-Fu Lee at Carnegie Mellon, who was one of my thesis advisors, came up with this large vocabulary system with these context-dependent units and all these things. Since then, it's been like a gradual trickle of 5% relative here, 5% relative there. So this is just to say when Lee and Dong came to my office and showed me this number, the first thing that I said, oh, check your results. There must be a bug. Normally the bugs are such that your errors are higher, but there are some times where your bugs are, you have lower errors because you are looking at the directory that has the correct transcriptions for some things, and you think that that's the, so I said, well, that's too good to be true. Double check it. When there, I even had to go and check it. I said, oh, this seems right. So maybe there is something here. So up to this point, I was quite skeptical, but it's good to let good researchers have the freedom to go and explore different things, sometimes at least, and they have good intuition. And after this is when I started learning a lot more about the technology. So, well, if any time that you see something like this, there may be more where that came from. This is not that we are done. This is just the beginning of a new era. Just to be fair, if we use more training data on the baseline, on the traditional baseline, we get something that is similar. This is meaning, well, we shouldn't chant victory too quickly, but if you use more training data, we know more training data generally is better. It should benefit everything. So you might say, why didn't we put a column here with this technology, train with 2,000 hours, right? Why didn't we do that? Well, it turns out that even though the computers have gotten a lot faster in the last almost 2 decades since the first, the classic period in the late 80s and early 90s, this was still quite slow because they were using a much smaller database back then. Now the database has also grown to 2,000 hours. So yes, Moore's law has helped us, but still was hard. So what we had to do is use GPUs. So most of our algorithmic work had been done using traditional PCs, basically. In fact, not just traditional PCs, but just the CPU, the Intel chip in the machine. And what we found out is that that was slow even for handling a lot of the things, because you have more machinery, you push the boundary, more distributions, more states. So what we had to do is purchase a bunch of GPU cards, like the high-end NVIDIA cards that have the heat sinks that is like as big as my fist. We had to move this and buy a special air conditioning unit because it was getting the room very hot. Like it would be good in the wintertime because you don't need heating at that point. So that's why it took us a while. Just this is going back to hardware infrastructure. Normally, I hadn't heard of this, just more machines. Yeah, they go to the lab, who cares about that? Well, we came to a point and said, well, this seems like it's hot, but we need a new set of computer infrastructure just to handle it. And now we have a bunch of these GPU cards. So that's another thing that we had to do. So we use this switchboard task here because we thought, well, this is like a publicly acknowledged task. So if we publish results on this task, everyone, all the reviewers, everyone in the community will know what we're talking about. But we also wanted to know if it worked well in some of the tasks that our product group was interested in. That's part of the things that we do too. So we use 2 tasks. One of them is voicemails, voicemail transcription, and some other task, teleconference. It doesn't matter what it is. Just to say that there are tasks that our product team care deeply about it. So we did the same thing. We trained, and we saw 22, 26, 28% on the different relative improvement. So maybe not as big as this, but quite substantial. So at that point, we got the validation. So, well, there is definitely something here. So to summarize, what this work has proven is that this context-dependent deep neural network HMM hybrid scales to benchmark data. Oftentimes what I see when I review some of the papers is someone tries a new algorithm that maybe sounds kind of interesting on a baby task. It works on a tiny, tiny tasks. And that's good, but there's often times where you try that algorithm with a database that is much larger, what people are interested in, and all the gains that you have wash out, because now you have much more data, and your simpler models, you can train them and do just as well. But this is not true here. For the bigger tasks, we got even bigger increases. So again, that was one of the first times that I saw that. Typically, when you have more training data and more parameters, the gains decrease, and just everything blurs with each other. So why did this happen? I mean, I'm always interested in history so that we don't repeat the mistakes that we did in the past. Why did it happen again? I'd say the number one reason is, even if we hadn't done anything new, in the early 90s, people kind of gave up because just the computation wasn't there. I mean, you had something, it just wasn't there. And now, 20 years later, with Moore's law helping, now we have computing power that allows us to do this. It was, for runtime, it's not a problem, it's for training. These algorithms are very computationally intensive for training. And the fact that we have much faster computers, including GPUs, means that now we can train them where before we couldn't. So that's still, maybe there's like something that it was a good idea and was in hibernation for a while, and now. By the way, that reminds me of an example. I was talking to Vishnu et al. From the famed Bell Labs, probably like, I don't know, at least a decade ago or more. And he was one of the inventors of CELP, code-excited linear prediction. I don't know if you are familiar with this, but that's essentially, if you are using a cell phone, you're probably using that algorithm to compress the speech and encode it through the network. So when he first developed it in 1980 or 81, he told me, oh, we didn't bother filing a patent for it, because to encode and decode 1 second of speech, we had to use the entire mini computer that we had in the lab for 2 days. So I said, well, that will never be practical. Guess what? Yes, in 1980s, it's not practical, but there are not very many cell phones at that point. You fast forward 15, 18 years later, and yes, it's practical. You have it, the power in your pocket, right? So sometimes there is like a good idea, and it doesn't work because it's just ahead of its time computationally, not because it's not a good idea. If you wait, of course, it's easy for me to say that. You may say, well, I need to get my PhD or my next project right. I don't have the luxury of waiting 20 years. But sometimes that's true. Like the basic algorithm, after a period of time, can improve. The other thing is that the fact that you have a faster computer means that now you can run more experiments. So the same old experiment and configuration might still not work. You might just get the results more quickly. That's not good. But because you can run more experiments, you can say, well, how about if I do that instead? How about if I do this instead? And you can run many of them, and now one of them will work. Before, you had to really think very carefully which is the experiment you were going to run, because that was it. And you need to tell your friends, please don't unplug the machine, don't do anything, hope that it will not crash, and just send it. Now it's okay because it takes much less time. So you can run more experiments, and one of them say, aha, that's the one. So that's the power of computing helps us run more experiments. And I think that was probably still the number one thing. It's a little bit disappointed because we like to scientists, we like to say, well, it's because we have a new algorithm. And that's true also, but I don't think that was the number one factor. The number one factor is more computing power. That said, because we could run more experiments, there were a few algorithms that had not been proposed before, or variants, that stood up. So one example is we put the network directly to model these triphone states. Back in the early 1990s, people have tried that for context-independent phones, possibly because they hadn't had the luxury of running many experiments. So I'm not saying this is a super, I mean, once you think about it, that idea is very simple. And you know, there are a few other things. But even then, we have to keep in mind one thing. We have much faster machines, but still slow. We need to buy these cumbersome machines that we cannot put them in a server rack easily because they use all these GPU cards and special software. So there is still, it's not like I'm satisfied that, oh yeah, computation is not a problem. No, it's good enough that we can run these experiments, improve it on benchmark type data, but it's not necessarily good enough that we say, oh, we're done. And there are two ways. One of them is just wait. There will be faster NVIDIA cards and faster Intel chips. That's one possibility. And yes, we definitely want to latch onto that. The other one is Now there is an opportunity to try new algorithms that may be better computationally. This is the other problem, and maybe they are related. These things will still get stuck into a local optimum. It's less big of a deal, typically, because if you initialize it with this RBM technique, it converges to a much nicer place. It doesn't use this sigmoid, which means that you only look at the gradient in a small region, non-zero gradient, whereas the rest of the time, the gradient is zero. So you're trying to get, and you're stuck in an optimum you can't escape, right? So this is still a problem, less of a problem, but still a problem. So both of them are less of a problem than before, but still a problem. So I think this is a very rich area of research, and I'm very bullish now after 22 years with that picture where I was very hesitant about using neural networks. I hope that you believe me that this is something worth considering. And I don't know what your research is these days, but these techniques have been very successful, not just in speech. Our lab has been leading the pace in using this for speech. And now you see the number of papers in the recent ICASP and more recent conferences. There are lots of papers on this space. But also in image processing. Again, it started with Jeff Hinton doing this work on the handwritten recognition tasks. And this is an area where you are doing image, video. There's a lot of interest in using this type of techniques. And now that we have a better understanding of the theory and results across many different tasks, a lot of researchers are jumping in. So if you're looking for a topic for research, this may be a good one. So just to finish, I would like to conclude with, as I mentioned, after we got these results, I've been more interested in neuroscience. I always found it a fascinating topic, but I was always too busy to even look at it because there was also always something else to do. But here I said, well, now I have a reason to look into this. And natural or artificial? Well, at some point, I wonder, now that I have a better understanding of artificial neural networks, there could be cases that are better than natural human networks. There are cases where they're worse. And the reason is I ran into this test. There's all these studies showing given tests to high school students. And at least in the United States, apparently this was a popular problem. You see this problem for high school? This triangle, 4 centimeters, 3 centimeters, and x, find x. Well, of course, trivial for you. But for many high school students in the United States, it wasn't so easy. This is a very typical answer. Clever, huh? So you could argue that our artificial networks might do better than this. Here's another example. What is the language spoken in Latin America? Any guess of a popular answer? Yes. So I could imagine that artificial neural networks might be better than natural, at least in some cases. But at the same time, airplanes don't flap their wings, or at least today's planes don't do. I managed to find a picture of an old one that did, and they can fly. So it doesn't mean that we need to mimic completely. If we're going to build an artificial system, a computer system, it doesn't mean that we need to build it exactly how the human brain works. But it's still helpful, given that we have these techniques that work quite well, to understand some of the fundamentals, to see what makes sense and what doesn't make sense to adopt. This was, again, my position back in 1990 when I said, I don't believe we need to do things because of this reason. But it's also true that maybe planes fly faster than birds, not using their techniques, but there are lots of areas, especially in artificial intelligence, where humans do still better, with a few exceptions, okay? So it's still, we need to be having a balance. We need to see what is it that we need to do, learning from how the brain works, which for artificial intelligence tasks has proven to be a very good system. And at the same time, be practical and say, well, it doesn't need to copy exactly things, especially if we don't understand it. That's why I switched. So, well, now I'm happy to do these neural networks because I understand there is a probabilistic formulation behind it, which allows me to do maximum likelihood estimate of this, or many of the other techniques that we learn in machine learning that now you can use there. And that's why it's, well, I don't need to use exactly how the brain uses it, yet I know maybe how we can do the balance. So in human intelligence tasks, artificial neural networks may be better than natural ones one day. But for now, we still need to learn a lot from the human brain. For example, things that I'm wondering about. I mentioned at the beginning that the neurons have some randomness in it, meaning you put some fixed inputs and the output is changing depending on just the spikes, which way they're going. Is that just the fact that it's not implemented using a circuit, but rather implemented biological and chemical processes? That could be the reason. So that's maybe the thing not to copy from the airplane, perhaps. Or maybe it's Darwin. It's part of the evolution. And there is something intrinsic in this randomness that makes our human brain converge and not get stuck into a local optimum. Maybe, right? So it's hard to tell, but maybe this is not an accident. It's actually a feature. Also, local learning instead of backpropagation. If you talk to all the neuroscientists, they will tell you, backpropagation, it doesn't happen here. Maybe it happens in yours, but no. It's not something that happens in humans. All the learning is local, meaning it's the Hebbian rule. This neuron is just looking at what its output and what is its inputs. And based on that, it's changing the weights. It has no idea about the rest, other than for the fact that the rest are sometimes input to them, right? But our algorithms, typically we use this backpropagation, or even the RBM is still a global algorithm. So that still bugs me. Maybe it's not like we have the algorithm yet and there is nothing else to do. I suspect there is perhaps a possibility of doing local learning, which appears simpler, more distributed, and yet the power comes from the fact that we have tons of connections, way more. Like in all the systems that I mentioned, we have something like 10,000 neurons. Well, that's nothing compared to the 100 billion that we have in our brain. So maybe something simple, but lots of them perhaps. So there are lots of areas where one could explore. It's not to say we are done. This deep neural network thing is the new thing and that's it. There are many ways where there could be research, and we're doing some of that ourselves. So thank you. This is the first pass, the first talk. And I wonder if you have any questions, and after that we'll take a break. Any questions? Feel free to ask questions that aren't related to this as well, if you're curious. Yes?
I'm working with computer vision and have a reader knowledge on speech recognition. And it looks like you speech recognition researchers prefer the way of modeling rather than feature extraction as how to build the experiment task. It looks like you are the machine learning researchers. And, how do you think about so how can I say, feature extraction, or how to build a good experimental settings, or other than modeling a statistical?
So you're not as very involved in the speech recognition community. Like if you go to a speech recognition conference, you will see a lot of sessions on feature extraction too.
Okay.
What happens is that they don't do much. They don't move the needle very much. So I didn't talk about it. But people are trying because they feel, there must be a better feature. Let me try this, let me try that. But it's very ad hoc. Will you try one and see if it works? People have done a lot of experiments and noticed that it's hard to beat our current system, our current feature, MEL, frequency capsule coefficients, with delta and delta deltas over time, with like an HLDA, linear discriminative analysis transform, or PLP. And people are trying. It just doesn't go anywhere. That's not true for other communities. Okay. Like, for example, in the information retrieval community, if you come up with a good feature, it can really rescue you. It's like really big. But in our community, it's not that people haven't tried. It's just, I think we saturated over there. There is not much to pick. But it's true that in other fields, that could be an important space. And in fact, my colleagues in computer vision oftentimes are still getting mileage out of using, exploring the feature space. Yeah. And in fact, even in speech, one of the things that we've done is we use what we call bottleneck features, which is a deep neural network where we constrain At the first layer, we have many neurons. The second layer, fewer. The third layer, small, and then increase again. And we take the output at the bottleneck and say, well, that's my feature. And we pass it to a traditional HMM system. And we get gains too. But if you think about it, that's just kind of like cheating. It's like, well, this is the model. So those features are really good. But they are not obvious. They're just like, learn automatically through this deep neural network. So those are the only features that seem to have an improvement in the last 10 or 20 years. So at least in speech, there isn't really much that we know of, okay? There may be something there dormant, waiting for someone to find it. I would not recommend that, but I think that's okay. If someone is interested, someone could find it. I'm more excited, at least for speech, on the model itself. But it's true that in other fields, there's still a lot of mileage that you could get by looking at the features.
Well, I'm a bit curious about the decoding. When you change GMMs to a DNN, you still apply Viterbi decoding to
Yes.
the likelihoods, or
Yes.
it goes exactly the same? Or
Well, almost the same. Yes, at the very high level, yes, it's the same process. What happens is that a lot of the systems, to be real time, they pull a lot of the computations for the GMMs, and now you need to replace that, right? And that is more expensive to compute than a GMM, the neural network. But what we found is that computation, even though it's bigger, is more than before, because the models are sharper, you can prune more easily the other competing hypotheses. So overall, it's not slower. And incorporating, replacing one and the other is relatively easy to do. Conceptually, of course, once you start working on the code, it's not so simple, but conceptually. The thresholds, the pruning thresholds change, so you need to adjust those, but the code itself is not, it's relatively simple to add. Okay, so I think this is a good time to take a break. Thanks.